So thanks everyone for not running out. I know this isn't about the moon, but there is a nod to the moon in here. And so some of the inspiration for this work actually came from looking at lunar pyroclastic glasses. Anyway, so I'm going to talk about sort of an interesting Angrite. Anyway, so NWA 12774, if you're not familiar with Angrites, it doesn't matter so much. This is an interesting Angrite. It was found in 2019. And for Angrites, it has this interesting porphyritic texture. And so it has these large olivine phenocrysts and clinopyroxene phenocrysts set in this really fine-grained, quenched ground mass, which is sort of interesting. This is one of the only Angrites that looks like this. But even more interesting than that is the fact that there's these ubiquitous metallic inclusions present in both the olivine phenocrysts as well as the ground mass. And so here's just a couple of backscatter electron images showing these sort of spherical metallic inclusions inside some of the olivine phenocrysts. So on the left-hand side, you can see there's a rounded metallic sphere in one of the olivines, and then on the right-hand backscatter image, you can see there's one actually sort of in between, in this interstitial region, in between these two olivine phenocrysts, and they're generally spherical. And so these are sort of interesting because I've been doing some work with Chip Shearer on orange glass beads from Apollo 17, the pyroclastic glass beads, and there's actually a similar texture in some of the olivine phenocrysts in the orange glasses. You see these sort of spherical metallic inclusions in those, and so this sort of got me thinking about what maybe these textures and Angrites mean. And so the question is what can we learn from these? What do these mean? How do you get textures that look like this? And so just a little bit more about these. So here's just a couple of X-ray maps showing you what these little spherical metallic inclusions inside of the olivine look like. It turns out they're not, they're actually polyphase. And so if you look really closely, you can see most of the inclusions made up by camosite, but there's actually a little rim of troilite. And if you look really closely, I don't know if you can see this, there's actually metallic crystals growing from the troilite. In this case, and so in the middle there's a map of an iron K alpha X-ray map, and then on the right there's a sulfur K alpha X-ray map, and so you can see that the metallic globule sort of rimmed by what I think is probably a little bit of sulfide liquid, and so the inclusions are almost in the olivine are almost always spherical. They have a really consistent iron nickel ratio in the metal, so they're almost always about Fe95 to Fe90. The rest made up by nickel, and then there's always this little bit of troilite that rims these in most cases. And so I've sort of interpreted these as metallic melt inclusions, so to speak. That's the best sort of term I can come up with them, or come up for these textures. And so there's a few reasons I think that. So one, the inclusions inside the olivines and mostly in the matrix are almost always completely spherical. So this suggests they were liquid droplets. The other thing, and this sort of came up over and over, if you look really closely, you commonly see that there's almost always void space affiliated with these little inclusions in the olivine. And so I suspect that this is sort of a contraction texture, so sort of analogous to shrinkage bubbles and silicate melt inclusions. And so if you actually think about the crystallization of metallic iron, nickel, sulfur liquid, so when you crystallize, iron, nickel liquid to a gamma or body-centered cubic gamma crystalline camosite, there's actually about a 12% volume reduction. So that sort of explains these strange little void spaces. At first, I thought they could be vesicles. I'm not totally sure, but so that suggests that these were trapped in the liquid state. So when the olivine grew, this liquid or this magma was saturated in these metallic droplets or metallic liquid droplets. And so this also suggests, you can look at the phase equilibria for these. It suggests that the liquidus temperature for these olivines is very high, probably on the order of 1450 degrees C is my estimate. Anyway, so there's also type 2 metallic inclusions. These are the ones in the matrix. And so these aren't quite as spherical as the ones in the olivine. Always, some of them are, but not always. And so usually these are actually like little blebs of camosite that are encased completely in what I think was troilite liquid. And so here's just a map of some of these. And so these actually don't have homogeneous iron nickel ratios. And so it suggests that there was some compositional modification, perhaps via oxidation or some other process. So these are a bit different than the sort of primary inclusions in the olivines. And so this actually is a little cartoon I put together using the iron nickel sulfur phase diagram just to show you sort of the sequence of how I think these things formed. And so at high temperature, you probably have a metal saturated silicate melt that has these little immiscible globules of iron nickel sulfide liquid. And so as olivine crystallization proceeds, you actually trap some of these as melt inclusions. And so you can also see that there's an evolution in the composition of the residual metallic liquid. And so eventually you track up sort of on this ternary diagram, you track up towards FES saturation. And so a melt that may have had a few mole percent sulfur ends up crystallizing or ends up producing immiscible sulfide liquids. And so that's sort of the sequence as I see it. And so this actually brings up some really interesting questions. So why are these things there and what do they mean? And so I actually took some inspiration from the lunar literature here. So I told you there'd be a bit about the moon. And so Mac Rutherford had actually proposed that the metallic inclusions in the lunar pyroclastic beads are the result of some sort of smelting reaction where you have FeO in the liquid that interacts with a bit of graphite on decompression, and you can produce iron metal and CO. And so that was what he had proposed as the propellant for the fire fountaining of the orange glass beads was. And so this actually brings up an interesting parallel. So maybe that's what's going on here. And so then, the other question is, or the other potential hypothesis is that this just represents the partial melting of a metal saturated mantle region in the Angrite parent body. So it's not processed, it's just sampled a region that had residual metal in it. So that's also possible. And so there's a few ways we can discern between these two possibilities. And so the first sort of proposal by Mac Rutherford really depends on decompression. And so you can only oxidize graphite as pressure is lowered. And so as the orange pyroclastic beads were decompressed during eruption, you actually continued to oxidize graphite to make CO2 and or CO, and that's what actually drove the fire fountain. So it really relies on this decompression mechanism. But there's some emerging evidence in the case of the Angrites that these melts in particular probably crystallized at high pressure. So this is some geobarometry work that I've done that's in review right now. And so some of the preliminary or the results from this, if you look at the clinopyroxene liquid geobarometry, so it suggests that the initial crystallization of the olivine and CPX probably happened at 1.8 GPa or 18 kilobars. So these things clearly crystallized at depth, and so that means that the metallic liquid droplets had to form at depth. So you really can invoke a smelting reaction that calls upon decompression, sort of in the case of the moon. So something different's going on here. And so one of the possibilities that I think might be going on is essentially you're sampling perhaps a core forming alloy. So maybe this just represents a region of the Angrite parent body's mantle that hadn't experienced significant metal separation yet, and so perhaps these are core forming alloys. That's one interpretation. And so one crude way that you can actually test this hypothesis is we can actually compare the oxidation state constrained by this phase assemblage, and I'll explain this in a minute, compared to those that were sort of proposed from core formation models for the Angrite parent body. And so those were done by siderophile depletions. And so there was some work by Edgar Steenstra, and he suggested that the degree of siderophile depletion in the bulk silicate Angrite parent body suggested that the core segregated at about IW minus 1.3 log units. And so it turns out that this iron or camosite droplet olivine silicate liquid phase assemblage, you can actually write a univariant reaction or equilibrium between the silica component in the melt and the olivine crystals and the camosite. And so this little sort of phase diagram that I have up here essentially shows you that equilibrium. And so we know that our system has to be on this univariant curve on the phase diagram. And so I've done some thermodynamic modeling using melts and using the internal consistent data within melts. And so using this equilibrium, I basically calculated that, for the olivine composition that's present in the phenocrysts, you get about the FO2 of that phase assemblage is about IW minus 1.3 to 1.4. And then if you use a slightly more magnesium or a slightly more ferroan olivine composition, that goes up to about IW minus 1.1, 1.2. And so these are actually in really good agreement with the Steenstra data. And so this maybe does suggest that these really are remnants of what was a core forming alloy. And then I'll just leave a few conclusions up here. There's actually more questions than answers, so as there usually are. Anyway, so like the redox conditions from the phase equilibrium calculations suggest that these are consistent with the conditions inferred for core formation. So maybe these represent, essentially a source region that hasn't been depleted metal. So there are a few questions. So one question is, how do you get these little liquid droplets that are very dense and trained in these melts, and why are they erupted at the surface? I don't really have a good answer for that. That's a physical or dynamic process, but that's a good question. Maybe there's more hypotheses. These are just the two that I came up with. One drawing parallels from these lunar textures and the other not. Anyway, so I'll just leave you with that since I'm out of time.